Hi everyone, will be an overview of dark matter, some of the kind of getting into a little bit of the history of dark matter, of course, but then where are we presently? What are some prospects for the future? What don't we know? What do we know? What about modified theories of gravity, so on and so forth. So this will serve as an overview. First of all, dark matter is not really anything new, in the sense that for a good chunk of the history of astronomy, especially after Newton's equations, we were able to go ahead and detect the presence of material that we couldn't see via visible light. And so there were a few proposals. And one of the first ones I wanted to highlight was here on the bottom, where we began to predict and discover previously unidentified astronomical objects, thanks to understanding how gravity works. And of course, another famous example is the discovery of the planet Neptune, which was a dark planet. Previously, it was not seen by anyone in the history of humanity. And thanks to the equations of Newton's equations of gravity, basically we could predict very, very accurately where this planet should be because the orbit of Uranus was abnormal. However, it turns out that these equations were not the ultimate answer because an interesting thing happened because Mercury's orbit also had some anomalies. So, in a similar fashion to Neptune, perhaps there was another planet that just was too dim to see. So there was a planet, a hypothetical planet called Vulcan or something along those lines that would have been in between Mercury and the Sun. And that would have been one possible explanation for the anomalies in Mercury's orbit. But it turns out that really the solution in this case, well, was of course a modified theory of gravity. That would be the advent of general relativity that helped explain this anomalous orbit of Mercury. There is no planet in between Mercury and the Sun. And so that is a very interesting thing that will come into play. But of course, some interesting things we began to discuss, which was what are things like this? Here's an example of some dark clouds or dark nebula. Basically, you can see there are stars all over the night sky, and then there are these regions of darkness. What do they due to? Is it because there's a lack of stars there, or maybe there's something absorbing matter in the line of sight, something absorbing light? In the line of sight. Perhaps that's a case. And here's, of course, an example. Many times, to presently, we understand these to be basically dense clouds of gas, maybe sites of star formation, so on and so forth. But basically, the light would be getting scattered off. So there really is starlight behind these objects, but it's just a dense cloud of matter. But at the same time, this would be an example of dark matter. You can't see it visibly. And this was, of course, a big debate, especially towards the end of the 1800s. What is this? What object? Um, and it turns out that we had a pretty good idea that there was at least a good amount of stuff in in the Milky Way galaxy that we just simply weren't able to see. You could call this dark matter. Um, Now, of course, dark matter means something very specific today, which is definitely quite a bit different from how we had traditionally thought of dark matter, but this concept isn't anything new. Um, that there are a large number of bodies that we just simply can't see. So one of the first calculations was done by Lord Kelvin. He concluded as many as 1 billion stars might be dark bodies. Um, and others had similar conclusions. There was maybe some dark matter, maybe there wasn't. It wasn't quite clear in the early days, but generally there was some kind of amount of stuff, at least we could agree upon, that our best telescopes at the time were not able to see. Um, However, everything started to change several decades later with the advent of Fritz Zwicky studying the redshifts of various galaxy clusters, in particular looking at some galaxies in the Coma cluster. And so he was studying the physics of this, and it was very strange. He found that um, basically the cluster was orbiting way faster than it should be based upon its visible mass. The difference was he was, of course, adjusted a bit later, but when he first calculated, it was a very, very large difference, a difference of well over an order of a magnitude larger than it should have been. And so Zwicky, he concluded if this would be confirmed, we would get the surprising result that dark matter is present in much more amounts than luminous matter. And this was a great dilemma. By and large, it received in multiple ways, but it just so happens that some other astronomers, not too many, another is an example of Sinclair Smith, who found a good 200 mass to light ratio. So basically, that would be the calculated mass that we get from how fast these clusters are rotating, compared with how much light we see coming from such clusters. And so this was a really interesting thing. Um, and so it wasn't just Vicky who was figuring this out, but there were others, but there was no real resolution as to how could this possibly be the case. One early attempt was the famous, well, son of the famous Schwarzschild, Martin Schwarzschild, in 1954. He had this idea that maybe just the extra mass that they're calculating were just temporary visitors to such galaxies, but even correcting for such, that was essentially rejected. Another one that I had kind of glossed over is that to get the calculation of the total mass, it was the application of the virial theorem, because if which basically is related to, I encourage you to look that up, but it's relating the kinetic energy and potential energy together on average. Um, it's really interesting because it wouldn't apply if the clusters were really rapidly expanding and unstable, but that turned out not to be the case. And so one by one, essentially astronomers were left with a huge delay. And then to top matters off, this is another piece of evidence that let us know that there is a significant amount of stuff that we can't see within galaxies. But first, we have to talk briefly about galaxy rotation curves. So basically with these curves, you can go ahead and compare how fast a galaxy is rotating as a function of distance from the center of a single galaxy. Before, those previous few slides were on galaxy clusters, which was a handful of galaxies. Now this is a measurement on a single galaxy itself. And so we knew for a while that the Andromeda galaxy was rotating. There was really no problem. Um, some of the early estimates of the mass to light ratio was really high, from in between 100 and 6, and really it was refined to between 6 and 7. And there's an example on the right. There was a really good agreement. There's the two curves there, the observed and the calculated on the right. One is in red, one is in white. However, that began to change with the advent of radar, because it looks something like this, where now all of a sudden the measured curve, which is in white, appeared to be moving much, much faster than we calculated the galaxy should be moving based upon the amount of visible light. There just simply wasn't enough mass to hold these together. Here's a quote from Morton Roberts in 1970. If the data are correct, then there must be in these galaxies additional matter which is undetected, either optically or 21 centimeters. Its mass must be at least as large as the mass of the detected galaxy, and its distribution must be quite different from the exponential distribution which holds for the optical galaxy. So the question is, what is all this mass on the outer edges of galaxies in particular? It appears to be clustered in some kind of halo of sorts on the outer edge of galaxies. So here is a big we faced. And so we tried to compile this. So here's Roberts and Rotz in 1973 published this paper where they did this for several galaxies, finding that some slowed down as was suspected to be, but many did not. So basically, this was not some kind of anomalous effect. There was a significant amount of mass distribution in high radii. And so this is really interesting. So this was now that not just that galaxy clusters had a significant amount of dark stuff, but so did most galaxies. And there have been a number of measurements, we'll come back to this a bit, to measure how much of this stuff we see locally. And we can do that same type of thing, measuring solar system dynamics or measuring, yeah, that's one of the easiest ways to go ahead and do that, where you can constrain the density of this stuff locally. Any kind of anomalies in the orbits based upon the equations of general relativity, and you could simply add in a term, and you could do the same thing with dark energy as well, which in the next section. But an interesting question is, what is dark matter? Well, based upon, as mentioned early on, so there was, of course, Lord Kelvin, and basically it was stuff that we couldn't see, faint stars. It could be nebulous or meteoric material. Zwicky proposed it was in the form of cool and cold stars, macroscopic and microscopic solid bodies and gases. Another one was that, well, these aren't from galaxies, but they're from space itself. And so Penzias, who was part of the Penzias and Wilson team who discovered the cosmic microwave background, began searching for a bunch of free hydrogen in a cluster and set an upper limit that less than 10% of the required mass could have come from hydrogen gas. And essentially by 1971 that there was intergalactic gas or just free gas in various clusters could be rolled out as an explanation. Another one we'll take a look at were massive collapsed objects. So we'll look at many of these in more detail, M8 dwarf stars and other various possibilities, and all of them ended up getting rejected. We'll look at a few in particular as to. So, in terms of all the particles, neutrinos really were one of the most promising particles. Looking at the standard model of particles, really they have exactly the types of properties that you would need for what dark matter is. Basically, they're stable particles and they don't interact via the electromagnetic or strong interactions. And if they did, it'd be very weak. They were really first discussed in 1966, and Zeldovich, he was a very, very productive researcher. There, we mentioned him briefly with the Sunyaev-Zeldovich effect, looking at shadows in the cosmic microwave background briefly. But he made so many different contributions to Stephen Hawking thought that he was a collective author. Um, and so that was, of course, certainly a great compliment that he had accomplished so much that it really was, mind-boggling that someone can accomplish so much in a lifetime. But anyways, so again, neutrinos by the end of the late 70s were being discussed, and others began to explicitly argue, and this received a large boost whenever we measured the actual mass of the electron antineutrino. And the mass was around the type of order that it would have needed to be as well. So, I mean, this was really, really exciting. We began to come up with more robust ways to test our various hypotheses. And here's an example of some numerical simulations versus the standard model neutrinos. Basically, the idea was to test whether dark matter would be relativistic or non-relativistic during the early universe. And so, if you go ahead and look at the left column, that's an example of hot dark matter. The middle column would be warm dark matter, and the right would be cold dark matter. And the top row would be in the early universe, and then at the bottom would be the present day. So basically, depending on what dark matter was like, if it was hot dark matter, or if it was cold dark matter, and so on and so forth in the early universe. And so neutrinos in particular would have been hot dark matter based upon their mass. Especially as we got more refined measurements of the mass of neutrinos, it turns out that they were just far too light and they would have been whirling around at relativistic speeds in the early universe. And so basically the idea is that you could just compare the results of these simulations to the universe that we see. And so on and so forth. And just a summary of this. So on the left, if you looked at hot dark matter particles, basically at first they would collapse and form very, very large structures first. And then those large structures would break apart and form smaller galaxy-sized structures on the bottom. And then if you look at right, if dark matter particles were cold, and much heavier, they would have frozen out of thermal equilibrium much earlier. And basically, they would have formed a bunch of little small types of structures that only later would have merged into larger structures in the universe. So it's kind of like a top-down approach versus a bottom-up approach. also began taking big-scale surveys of the sky, and one of the first extensive one was in 1983, and this was really, really significant result. Here's a quote from relevant paper. We find the coherence length for a neutrino-dominated universe to be too large to be consistent with the observed clustering scale of galaxies. The conventional neutrino-dominated picture appears to be ruled out. Now, it's not fully ruled out because there could be perhaps an undiscovered fourth type of neutrino, a so-called sterile neutrino that could be, and perhaps that will be the case. But at least the three standard model neutrinos that we're familiar with are not dark matter. And here's an example of how you could think about that galaxy survey here on the right. So closer to the center is more recent, and going farther away from the center, out in the radial direction, is going back farther into the past. And what we see is that going back into the past, or the farthest from the center, um, on the outer edge of that circle, you see that they're really sparse structures. And then those structures start to form and become more and more intricate the more recent you get, which aligns quite well with the cold dark matter simulation. So basically, a large-scale galaxy simulation compared with measurements of the actual universe let us know some of the properties of dark matter. So that led to some more discussions. Well, okay, so neutrinos, they're really the only candidates. They were the only ones that are stable, electrically neutral, not strongly interacting. Um, However, it turns out that maybe there are more particles than those in the standard model, because there are no standard model particles that could make up dark matter. And we'll come back to the baryon proposal a little bit later on, how we know that dark matter is not made up of baryons. But there is the theory of supersymmetry. And while the idea in itself might seem a little bit strange for many people who either haven't read about it or aren't particle physicists, basically I've written here that it's the idea that for every fermion, a boson must exist with the same quantum number and vice versa. And that might not make a lot of sense. And I'm just going to give not much of an overview of supersymmetry. I'd encourage you to look that up independent of this. And it was a fairly promising approach because it was very interesting that particle physicists had been working on symmetry for some time. And just so happens that one of the hypothetical supersymmetric particles also happens to have the properties that dark matter would have to have. So in particular, the gravitino would be the mediator of supergravity interactions, just as the photon mediates electromagnetism. And this would be the particle that we would be most interested in as a possible candidate for dark matter. But it is a very interesting idea because it's not as if we were like, oh, we have no particles of what dark matter is, so let's go ahead and just invent something. No, this is something that particle theorists had been working on previously. And then it just so happens that one of the possible solutions also solved what is the dark matter question. And that's why this is a really, really exciting thing. But despite being the most studied candidate, there's presently no experimental evidence for supersymmetry. So what's another? Well, it turns out that axions also are a very, very interesting and promising idea. And this is also the reason why this idea is promising is somewhat similar to why supersymmetry is promising. And this comes in particular from the field or theories of quantum chromodynamics, which basically describes the strong force and how quarks and gluons interact. And it's a really, really remarkably precise and robust theory. Here's an example of a proton and antiproton collision, and some of the equations that go into the Lagrangian of quantum chromodynamics, and so on and so forth. And it turns out, though, that there's an interesting dilemma that QCD come across, which is that there is a problem. Now, it might not really be a problem, but we would want our most robust theories to describe as much as humanly possible. And there's one thing that quantum chromodynamics presently really can't explain, and it's something that's effectively called the strong CP problem. So basically, we know that because there's a big difference in matter and antimatter in the universe, well, there would have to be some kind of process involved in the areas of which quantum chromodynamics would be really relevant, um, that violates what's called CP symmetry. And C would stand for charge, and P would stand for parity, or the handedness or spin, and so on and so forth. So there had to have been some kind of violation of this in the early universe. Um, and so it's an interesting question. In quantum chromodynamics, didn't really have a natural way to account for that, unless one of the parameters in frameworks was rather finely tuned. Um, there, at least as I mentioned here before I get into what I mean by that, there has been some evidence of some CP symmetry violations. But at the same time, such evidences are not quite large enough to account for this particular. So one of the ways that you could account for that is within a particular framework, which is related to part of the Lagrangian. And there's this term, and it's really, really interesting. This particular, what is this? My goodness. Well, it's related to the phase of the QCD vacuum. It's a little complicated. This is not really my area. Um, so what was I going to say about axions? Okay, this is good. This is a nice summary of the Pecky and Quinn proposal. And there were a few, oh, I see. Okay. So basically, in order to get quantum chromodynamics to break CP symmetry, such a symmetry breaking implies the existence of the axion. So basically, oh man, this is a little bit out of my league. I would have to do so much reading, so you'll have to forgive me for this particular part. I would encourage you to look up axions and how they are potential candidates for dark matter. That's basically what I could come to at the end of the day. I'm not a particle theorist, so I don't even really want to try to do justice to this. But the point is, the other reason why this is exciting and promising is because the um, particle dark matter would just so happen to have properties within this particular theory of quantum chromodynamics, a subtheory really, that would also simultaneously solve a problem of quantum chromodynamics. So basically, again, this is a really promising approach that, again, currently doesn't have any experimental evidence. But at the same time, it was something that particle theorists were working on that also could solve the dark matter dilemma as well. So these are really promising approaches, but we're not sure about either of them yet. Kind of the main takeaway. Another, just kind of an overview or another possibility is trying to consider what kinds of properties such cold dark matter would have. So they could potentially be massive neutrinos. They would have to be undiscovered fourth type of neutrinos. They could be supersymmetric particles, but they could be axions. But basically, one of the unifying things is that there were certain properties that were pretty much well agreed upon. It couldn't be too light, and it also has to have a certain self-annihilation cross-section, which is really interesting, that just so happens to have a similar cross-section as the weak force interactions. And so this has led some attempts to go ahead and detect interactions of dark matter, in particular looking at weakly interacting massive particles. Essentially, this is a summary. So this Another possibility that was considered is that instead of being made up of WIMPs or any of these other more exotic particles, well, why not? Let's just really, really make sure that it's not made up of stuff that we're familiar with, particles that we're familiar with. So baryons is a great candidate, and this is similar to proposals from the early 1900s. Basically, baryons, protons, neutrons, etc. I mean, that's essentially the main mass of baryons. And so what could these massive compact halo objects be? Planets, brown dwarfs, red dwarfs, white dwarfs, neutron stars, so on and so forth. There are really two main ways to test this hypothesis. So here's an example of gravitational lensing, in particular gravitational microlensing, and I'll show you the type of signature that we are looking for. But basically the idea is that um, if you were looking at distant starlight and there was some kind of macho, some kind of massive object, you could get the intense and basically the increasing intensity or the focusing of starlight being bent around the macho. You'd get a signal that looks something like this. Here's a nice diagram of what we would expect from a macho event. So here are three different time frames. Here you see there's the macho that's going in between the star and the Earth. So you see here that we're measuring the intensity of starlight in the left frame, and in the middle one, the massive object is in between the star and the Earth, and you see it's bending the starlight around. And so if you look at the bottom, that should give us evidence of an increased brightness of the star. And then after the macho goes ahead and passes by, the signal will return to normal. And this was a really, really exciting thing. And so the first claim of an observation came in 1989, and really it was almost that the dark matter problem had all, for all intents and purposes, been considered solved. After this discovery of machos in 1993, that was one of the comments of a team member. There was a little bit of a problem because after looking at the light curves of 40 million stars, the first collaboration only found about 15 potential microlensing events. And then there was a separate collaboration that took data for even longer and only identified a single microlensing candidate event. So this doesn't mean that dark matter is not made of machos, but what it does tell us is that it places restrictions or limits on what fraction of the mass in the halos is made up of these massive objects. And essentially, it was less than 8% or so. And essentially, that was very, very strong evidence against dark matter being made up. So maybe a portion of the matter in halos could be made up of this, but most of it isn't. You could really know and rule this out, and not just in the scale of looking at the light curves from galaxies, but on the scale of the entire universe. If we could take a budget of all of the baryons in the entire universe, which is a really bold thing to try and do. But it turns out that we made a number of advances starting around the mid 1900s. And so an interesting question is, where did nuclei come from? Where did the nuclei of atoms come from? Sir Arthur Eddington and others began to argue in the 20s, well, that maybe you could have the fusion of hydrogen into helium in stars, and maybe even heavier nuclei as well. And so there was some significant work that was done leading up to the culmination of Fred Hoyle calculating nuclei as heavy as iron could be formed. And then there was at least some initial excitement about that, where all of the elements could possibly be made inside of stars. But that turned out to be greatly limited. And in particular, though, there was an interesting proposal. There was an alternative to some of the nuclei being formed in the early universe by neutron capture. And so there's a famous paper that was published um, and that was really refined. Um, and at first they claimed that in this earlier nucleosynthesis event, like a Big Bang nucleosynthesis event, you could produce all of the elements in the entire universe. But that's not true. We find that there is a very, very sharp breaking point. If you go ahead and take a look at it, between helium and heavier elements. So in the early universe, a really interesting result is that we would calculate that what should you get in the early universe? Well, you should get a certain amount of hydrogen and helium, and so on and so forth. But then you would stop too much after helium. You get a little bit of lithium, a little bit of beryllium that would decay into lithium, but that's about it. And um, here's an example of how the proportions of these elements formed in the original nucleosynthesis event depend very strongly on the baryon density. So basically, if there was much less baryons in the entire universe, than what we would expect to see. We would expect to see more deuterium and less helium in the entire universe. And so this is a really, really powerful type of measurement that goes ahead and lets us know if we can just simply measure the amount of hydrogen or helium or deuterium very precisely, we could know what the entire universe's baryon budget is in terms of its overall density. And so we go ahead and found some nice constraints. And here's an example that really lets us know that there can't be a lot of extra baryons hiding somewhere. Because, first of all, as we saw on the last slide, the amount of elements produced depends strongly on the baryon density, but so do the anisotropies of the cosmic microwave background. Here's an example comparing just a number of different simulations where you see that you get different peaks and different heights of the peaks relative to one another in the cosmic microwave background if the baryon density is much different. And so this combined with the microlensing lets us know that baryons, there can't be a lot of extra baryons in the universe somewhere. There's little room for significant amounts of extra baryons or machos, very consistent with the previous results. And so this is a really, really important result, that there are not a lot of baryons hiding. So this is essentially ruling out the standard model particles. But this is something that we really, really wanted to be sure of. Because instead of proposing exotic physics that we don't have any evidence for, which very well could be the next steps or the next more comprehensive theory of particle physics, we don't yet know yet. But we should at least for sure rule out the hypotheses that it is not any of the standard model particles. What should we do next? Well, how about we change gravity? Because if you recall thinking about the planet Vulcan, well, the problem is just that we needed better equations of gravity. And so maybe we just need better equations of gravity, that we're just simply, that gravity works a little bit different on big scales. And so as a result, we're just trying to explain something, but really there's nothing there to explain. It's just that our equations that are predicting or over predicting the amount of matter are wrong again. So it's a really interesting proposal. And one of the first proposals, and it was rather raw in its first form, but it's basically maybe the gravitational force is proportional to the square of its acceleration. And this it would still converge to the F equals ma as we see here on Earth, but and it had a lot of problems in terms of how it violated the conservation of momentum, angular momentum, and energy, and there wasn't really a way to integrate it with general relativity. But this was a very interesting idea, and I think this is a great example of proposing any hypothesis and then working it through, doing the hard work to work it, because there's a lot of hard work. Really, the first serious proposal of modified gravity or theories of modified gravity came with the combination of two cosmologists, Milgram and Birkenstein, and they essentially wrote a Lagrangian of Newtonian gravity rather than starting with the second law, which basically guaranteed that it would be consistent with other laws of physics, but it still wasn't compatible with general relativity and couldn't really, and what I mean by that is it couldn't account for things like gravitational lensing and the cosmological expansion. So basically that's a problem. I mean, while it's great that you come up with a new theory that doesn't actually break all of the other theories that we've tested really well, so that's good. That's a good first step, but you still have to account for the evidence. So then we came up with relativistic Lagrangian theory, and that worked really well. And then there was, but it still didn't describe some potential observations. And then there was, of course, the Tevis theory that had solved many of these issues and could account for gravitational lensing, but still had a number of problems. There's something that all of these tend to not be able to describe, which is, we'll see more in a little bit. But it turns out that there were also some observational successes of modified Newtonian dynamics. Basically, it of course could explain the observed dynamics of many galaxies, which in some sense wasn't so impressive because it was essentially an empirical fit to go ahead and describe this. But it also did make predictions of particular galaxies that were found to be compatible with MOND, which is really, really important. If it's onto something, MOND might be onto something. And it's still compatible with rotation curves for hundreds of spiral galaxies and can provide an explanation for this empirical Thule-Fisher formula that's here on the right that talks about the intrinsic luminosity and rotational speed of spiral galaxies. And so this relationship provides a little bit of a challenge for dark matter because it's basically that, well, it turns out that the rotational velocity or average rotational velocity of galaxies corresponds to how bright it is. And so that's a very, very interesting result that basically kind of it seems like a little bit of a challenge or almost contradiction with some of the results from dark matter, which you recall that their rotational speeds as a function of distance required a significant amount of stuff that we couldn't see. But on average, it turns out that galaxies tend to follow this Thule-Fisher formulation, which is really interesting. We'll come back to this and some of the strengths of MOND. There are a number of challenges to modify Newtonian dynamics. And here's an example of two merging neutron stars. Some of the early models on the scale of galaxy clusters, they still required significant quantities of dark matter. And so one of the potential solutions, of course, would be massive neutrinos. But again, we don't have any evidence of that. But then there's some interesting results here. There's a rather bold type of claim, but sometimes you find some really bold claims, various competing groups. But it was observations on gravitational waves also potentially rolled out all modified theories of gravity that are designed to dispense with the need for dark matter. And so that might not actually be true. We'll have to see how this is, but this is a really exciting thing because essentially if there are possible competing models, one of the best ways, of course, to judge between them is to get more data. And so this is a rather dramatic claim that gravitational waves rolled out all forms of modified gravity that have no dark matter in them. So very interesting. And things started to really change and the discussion was transformed in 2006 with the advent of this paper that was a direct empirical proof of the existence of dark matter, a very, very bold claim, in which we began to go ahead and measure amounts of dark matter. Here's an example of a famous one that for many cosmologists saw this as the death to theories of modified gravity. Now, this doesn't actually represent the death of modified theories of gravity, but it was a very interesting result where if you go ahead and use the similar principle to gravitational microlensing, but you now do this with gravitational lensing, you can tell where a significant amount of mass is contained within galaxies. This is a cluster of several galaxies, the bullet cluster in particular. What you see here is that the area in green is showing where the bulk of the mass is located. But the remarkable thing is that the bulk of the mass in the bullet cluster is not contained where the visible light, the bulk of it, is located. So the colored map is the X-ray image based upon where the bulk of stellar activity is coming from. And so that's a very, very interesting result, letting us know that, again, the bulk of matter is not where the visible matter is. There's a significant amount of matter not contained in the. And so basically this is a description, and surely this would be the death of MOND, because this was very strong evidence. There's significant amounts of dark matter. We can measure how much stuff is there. And also MOND was not able to describe the peaks of the cosmic microwave background, which essentially is the most precise thing we pretty much ever measured in the history of the universe. However, it's not the death of MOND, because there was a really interesting paper published recently that was proposing that, well, actually, guess what? There's a rather astounding result looking at the observed centripetal acceleration plotted against the distribution of baryons, where again you find some kind of relationship. So this should really not be the case if there are significant amounts of dark matter, where you basically can account for, because we know dark matter is not made up of baryons. Again, if you add up the total mass of baryons, it shouldn't really correspond too directly to the observed acceleration in various galaxies. And this would be a measurement of this would be related to the speed that objects are. Of course, the centripetal acceleration is equal to the speed squared over the distance from the center of rotation, um, and is very interesting. And so this fought back and said, this is another remarkable where you only need to pay attention to the normal matter to figure out the rotations of galaxies. This is somewhat similar to the Tully-Fisher relation. So this is kind of funny that it's almost like a heavyweight boxing match, if you will. Here is another comeback paper, and it's going back and forth, and this is really exciting. Here is a rebuttal to the previous paper that was absence of fundamental acceleration scale in galaxies, where they said, now I can reject the various theories of Mond at a confidence of over 10 sigma. And so if you were, just curious about this, I would just keep your eyes on this paper and then the rebuttal papers and really see what ends up happening. This is a really interesting result. And of course, it'd be cool if both of them could be true, but not, now, of course, how could that be the case? Well, I'll talk about that here in a little bit. I'll get to that, but not yet. But of course, that's a wonderful claim that at about 10 sigma, that'd be about 99.9999999999997% confident that modified Newtonian. But of course, that would be a good reference to Dumb and Dumber. So you're saying there's a chance. So let's go ahead and piece some of these parts together because this is a really, really rich story, and it's hard to do justice to what the physics community has done on this topic in the past, really over the past 100 years, and making many uh, advancements in recent times. And so just kind of recapping, there were some early attempts to measure the amount of dark stuff in our galaxies. The main conclusions there likely was some. Things really picked up and were transformed with the discovery of significant amounts of mass in the coma cluster that we couldn't see, and so on and so forth. And we didn't really link this together to individual galaxies until the first measurements using radio astronomy of galaxy rotation curves. And basically all kinds of standard model solutions were rolled out one by one by one. And ultimately it took several decades to rule out the last bit of them. But by the 70s, it was pretty unanimous that there was a significant amount of missing mass in galaxies. And the community had been won over. It took some time. Here's an example of various mass to light ratios, looking at some different galaxies, and these types of results were really, really significant in helping win over the community. And why was that the case? Well, because evidence. Evidence is key. You need evidence. Lots and lots and lots of evidence. And I think it's really a neat picture, and this is not something that many people just wanted to accept. Hey, there's a lot of stuff made up of a particle we don't know contained all over the entire universe, and the density of this stuff just so happens to be a good 5 times greater than the density of normal matter. That's really, really interesting. And so, but it took a lot to win over the community, and I think that's process. And then there were some considerations from cosmology as a whole. So those were largely focused on just measuring properties of galaxies and properties of clusters of galaxies and so on and so forth. Here's a quote: "A variety of arguments strongly suggest that the density of the universe is no more than a tenth of the value required for closure. Loopholes in this reasoning may exist, but if so, they are primordial and invisible, or just black." And so this was an interesting result from calculations of the required mass for the universe to be flat, which we'll come back to. And a significant amount of mass seemed to be missing. This was a really, really great mystery based upon the density of matter. And inflation in particular began to transform how the cosmological community began to think about the early universe. And it turns out we were able to make specific predictions about the density and the spectrum of density perturbations, which we'll come back to. But here's a rather significant result. These are regarding the anisotropies of the cosmic microwave background. And Peebles wrote a really effective paper in 1982 arguing that baryons alone are insufficient to produce this power spectrum. And this is why one of the strongest evidences of dark matter really is contained on this single slide, or just summarized on this single slide, which has to do with the anisotropies of the cosmic microwave background. On left is what the anisotropies look like with dark matter, and on the right is with just normal matter. Cosmic microwave background looks like this. And so this is a really, really profound and significant result, where no matter how much we want to avoid this, we cannot explain why that third peak there, or really the second small peak, is so large without significant amounts of dark matter. And this is a really, really profound and significant result. It's hard to do justice to how important this particular slide is, and how influential it is in thinking. And again, some summaries from numerical simulations. We learned, of course, quite a lot from them. One of the first ones, I just had to give a little shout out to this. This was really impressive. One of the first simulations was done by Eric Holmberg in 1941, where he got 74 light bulbs, photocells, and galvanometers. And basically, he set it up and calculated how much light was received by each cell, and then moved the light bulbs in the direction that received the most light. And the reason why this would actually work is because the intensity of light decays like an inverse square law, and gravitational interactions decay like an inverse square law, at least in weak gravity effects. And so it's a really, really brilliant idea, and he did these simulations calculating interact. And again, a summary of those simulations, well, they became increasingly important starting in the 70s. And we found, of course, that their galaxies would have been unstable unless there was some kind of halo of material that was later confirmed by measurements. And simulations, the great thing about them is they don't really depend on what dark matter is. It just simply depends on whether or not it would be hot or cold, kind of what their overall mass would be and how strongly interacting they are. And so these simulations were really great, and they worked really well, describing many things about the universe, and there's a link to a more recent universe simulation. So we have a really good idea about what our universe is made up of. Basically, the point and power of simulations is that if you have these models and you let your models run, and it turns out that your models either predict things or, just more broadly speaking, they match the actual universe that we see, that would give you a good idea that your models are based upon something, well, real, and they're at least a close approximation to the universe. And so kind of just even taking a farther step back, this is a series of broader and broader ideas. Dark matter is really transparent, first of all. It's not dark. It doesn't emit or absorb light. It doesn't interact with light at all. So it's transparent. So really, transparent matter is probably a better name. But dark matter is just kind of the one that was inherited because of the ways that it was initially discovered. That there are significant amounts of matter that doesn't interact with light, i.e. dark, but it's not actually really dark. And then the reason it's called matter is because its energy density decreases with inverse volume. And we'll talk more about that when we come to dark energy and why that's significant. And it rarely interacts both with itself and with normal matter. How rarely, we don't know. The main evidence is basically galaxy clusters, galaxy rotation curves, gravitational lensing, the cosmic microwave background, and large-scale structure formation. And without dark matter, galaxies are too fast, stars are too fast, galaxies bend light too strongly than what visible matter can account for. The cosmic microwave background doesn't come out right, and structure formation starts too slowly. So you have all kinds of things that dark matter goes into it's why there's not really a question over. But there are some weaknesses to dark matter as well. This Thule-Fisher relation. It could just be some kind of manifestation of an interaction between visible matter and dark matter, but it can't really be described mathematically. And that's, of course, an interesting question. There's also this interesting question of galaxy cusps, where you find density peaks and galactic centers in various calculations or simulations, which doesn't match our observations of where dark matter is generally located at. It also predicts too many dwarf galaxies, and it turns out MOND actually works better for each of these in particular. But it can't explain the cosmic microwave background, the early universe, or galaxy cluster physics. Is there some way to unite the two? Maybe. Here's an interesting hypothesis I think that is potentially promising, which is where maybe dark matter actually has two phases and similar to a superfluid. So it has a normal fluid phase and a superfluid phase. In the normal phase, it just basically explains, it would act like a particle, like particle dark matter. And that would help explain how galaxies form, galaxy rotation curves, the cosmic microwave background, and so on and so forth. But it could have some kind of superfluid phase at low temperatures. And basically, the fluid would condense, and there would be the production of phonons that would look like modified gravity. So this is a really interesting thing. Studying superfluids, you can get this excitation that happens within superfluid-like matter. And what would this look like? It would look really similar to how we describe modified gravity. And this is another really cool, potentially revolutionary idea that dark matter just simply has two phases. Especially as it gets cooled down on the far outer reaches of galaxies, it would enter the superfluid phase, and then that would give us a modified gravity effect on the outer regions of gravity or galaxies. But it would behave like particle dark matter in terms of explaining the cosmic microwave background in the early universe and so on and so forth. Really, really interesting idea. Um, and then a few other things, just some recent things. There's, of course, the galaxy that may or may not have dark matter at all. This one made some ripples, if you will, that would have been a really interesting result because if there was a galaxy that contained no dark matter and our equations of general relativity describe how the physics really well, that would give us confidence that on big scales, it's not that our equations of general relativity need modified. And so for many, this was seen as some more strong evidence against MOND, but of course this could fit fairly well with various theories of MOND as well. So we'll see. Another cool measurement, this was dark matter on the move, where basically here was a team that measured the amount of dark matter in active and inactive dwarf galaxies. And we found a really interesting result where we went ahead and found that whenever dark galaxies had a really active centers, the dark matter tended to be found in halos on the outside. However, in those that stopped forming stars, the dark matter tended to be clustered more closer to the center of the galaxies. And so that would be a really interesting result that shows perhaps a way that dark matter could move that we were previously unaware of that would help explain why we see these halos in the first place. So that was a really cool, interesting result. And there's just a lot of really, I think, really fascinating and promising ideas that are out there, but we still don't know a lot about dark matter. And at the end of the day, even if we have dark matter, there's still a significant amount of stuff that we can't account for the universe to be flat. Having all of this, about 30% of the critical density of the universe could be accounted for. And so, where does the rest of the universe's energy density budget come from? Well, we don't know, so let's call it dark. And since it's an energy density, let's call it dark energy density. We'll come back to that here soon. Here's just an example of, of how the amount of dark energy would significantly impact our universe. We'll come next time. But of course, this is a good excuse if you're ever late for something because the universe is continually expanding and it's now accelerating in its expansion. Now that actually wouldn't impact us overall, and it's not like your atoms are being pulled apart, because while this is stretching space apart, the interactions between yourself and gravitational interactions are so much stronger than this on small scales that you're not actually expanding. So this isn't a good excuse, but it was kind of a funny little comic I saw one time. So anyways, let me know if you have questions or if a part was unclear, and yeah. Take care and happy learning.